This is a technical refresher on parallel RLC circuits, focusing specifically on their mission-critical function inside modern aerospace systems. A tank circuit is defined by its function, not just its components. Think of it as a self-sustaining energy exchange system. Its entire behavior is governed by the physics of electromagnetism and dielectric polarization, which enables that cyclical transfer of energy between two very different physical states. Now, analyzing parallel topologies demands a fundamental shift in our mathematical framework, moving away from the conventions used for series circuits. Remember, in series circuits, current is the constant, which is why we use Kirchhoff's voltage law and mesh analysis. For parallel networks, everything changes. Voltage becomes the constant parameter. This requires us to apply Kirchhoff's current law and nodal analysis so we can accurately map the vector sum of all the branch currents at common nodes. Because of this, impedance isn't calculated directly. Instead, it's derived from the total current. Honestly, impedance is a pretty inefficient metric for parallel analysis. The superior mathematical tool is complex admittance, which is just the reciprocal of impedance. Admittance, or Y, is made up of a real part, conductance, G, and an imaginary part, susceptance, B. This structure is perfectly designed for calculating the vector sum of parallel branch currents. So let's examine the physics that govern the high-efficiency energy transfer that actually defines the resonant state inside the tank circuit. The core mechanism of resonance really involves two distinct and opposing ways of storing energy, both operating in a cyclical, self-sustaining exchange. First, the capacitor. It stores potential energy in an electrostatic field through the dielectric polarization of its core material, something like tantalum pentoxide. This process makes the current lead the applied voltage by a precise 90 degrees. On the other hand, the inductor stores energy in a magnetic field. It's governed by Faraday's law, and it generates a counter-electromotive force that causes its current to lag the voltage by exactly 90 degrees. These precise opposing phase shifts are the absolute prerequisite for resonance. So, at that specific resonant frequency, the 90-degree leading capacitive current and the 90-degree lagging inductive current are exactly 180 degrees out of phase. Now, according to Kirchhoff's current law, their vector sum at the circuit node is 0. This cancellation leads to a minimal line current being drawn from the source. But at the same time, it creates a massive self-sustaining circulating current inside that closed LC loop. A circuit's selectivity, its ability to pick out one specific frequency, is quantified by what we call the quality factor, or Q. For a parallel RLC network, Q is defined as the ratio of the parallel resistance to the inductive reactance. A higher Q factor means you have a more efficient resonance, which directly translates to a narrower, more selective bandwidth. Look, the series impedance formula shows the direct subtraction of reactance values. That approach is completely invalid for parallel circuits. In a parallel topology, we don't subtract reactances. Instead, we analyze the vector sum of the branch currents, which are themselves governed by those reactances. That is the critical analytical distinction here. These theoretical principles aren't just academic. They're deployed as tangible, flight-critical hardware inside modern aircraft's communication and navigation systems. A perfect application is the pre-selector filter for the VHF comms receiver in a Garmin G1000 class avionics suite. A wideband RF signal comes into the unit. The internal parallel tank circuit is tuned to the specific resonant frequency of the channel you want, let's say 121.5 MHz. At that exact frequency, the circuit presents a near-infinite impedance, which forces that signal into the low-noise amplifier. Meanwhile, all the other off-resonance frequencies see a very low impedance path and are just shunted directly to the airframe ground. This effectively isolates that one single channel you wanted. Now, the severe operational environment of aerospace, which is quantified by standards like RTCA DO-160G, mandates components with very specific material compositions and a resilience to known failure modes. For example, MIL-SPEC 15305 inductors use ferrite cores and are encapsulated in epoxy. Their primary failure mode is an open circuit from a wire fracture. On the other hand, MIL-SPEC 39006 wet tantalum capacitors use a sintered tantalum anode and a liquid sulfuric acid electrolyte. They require voltage derating above 85 degrees Celsius, and their main failure mode is a catastrophic short circuit from dielectric breakdown and electrolyte leakage. Beyond those standard failures, two industry-specific threats are everywhere. First, tin whiskers. These are microscopic, conductive filaments that literally grow from the pure tin plating that was mandated by ROHS directives, and they cause shorts. This is mitigated in aerospace by exemptions for using tin-lead solder. Second is the problem of counterfeit components, which is governed by the AS 6081 standard. Component obsolescence forces procurement into gray markets, where old parts are harvested, remarked, and sold as new, a critical threat to system integrity. Effective troubleshooting at the bench level requires absolute fluency in schematic symbology and the precise interpretation of how circuits behave under fault conditions. A technician has to be able to differentiate between ANSI and IEC schematic standards. The ANSI symbol for an inductor with a ferrite core is a series of loops with two parallel solid lines. But under IEC 60617, that same component is shown as a solid filled rectangle, which, as you can imagine, is frequently misinterpreted by inexperienced technicians as a resistor symbol. So let's consider a diagnostic scenario. You have a parallel RLC circuit and it's operating precisely at its resonant frequency. Now, a temperature drop to -50 degrees Celsius causes the capacitance to decrease by 10%. What is the immediate effect on the total line current? The total line current is going to increase. Here's why. At resonance, line current is at its absolute minimum because those reactive currents cancel each other out. That 10% drop in capacitance breaks the XL equals XC equilibrium. So the circuit is no longer resonant. This introduces a net reactive current, IX, that is no longer zero. Therefore, the vector sum for total current, IZ, has to mathematically increase from its minimum value. In aerospace engineering, resonance is not some abstract theory. It is the functional intersection of quantum mechanics and metallurgical integrity. And it's at this intersection where the failure of a single passive component, whether it's driven by environmental stress or supply chain corruption, can directly compromise mission success.